For more than a century, physicists have treated the speed of light as an absolute wall. Nothing moves faster, not matter, not information, not anything. Then, in 1994, a physicist studying Einstein's equations found something deeply unsettling. The equations did contain a way around the limit, not by moving a spacecraft faster than light, but by moving space itself. At first, the idea sounded impossible, a loophole hidden inside the same theory that created the speed limit in the first place. But the mathematics worked, and what made physicists take it seriously was the fact that the universe is already doing something very similar right now. Galaxies at the edge of the observable universe are receding faster than light because space itself is expanding between them. No physical law is being violated. Einstein's equations allow it completely. Then things became stranger. NASA funded real research into the concept, a theoretical drive based on compressing space ahead of a spacecraft and expanding it behind. At the time, the required energy appeared absurd, roughly equivalent to converting a planet the size of Jupiter entirely into fuel. Then later calculations reduced that estimate dramatically, and in 2021, a peer-reviewed paper proposed that at least part of the effect might work using ordinary matter alone. Not science fiction, real physics. The unsettling part is that the loophole has now survived decades of scrutiny without fully collapsing, which raises a question physicists still cannot answer cleanly. If the universe already allows space itself to move faster than light, what exactly is stopping us from learning how to use the same mechanism ourselves? Before we go any further, if you enjoy exploring the cosmos with us, a quick like or subscribe goes a long way. It helps us keep making these deep dives for curious minds like yours. Let's talk about what we actually know. In the spring of 1905, a young patent clerk spent his evenings thinking about clocks, not engines, not rockets, clocks moving beside trains, clocks carried through empty space, clocks observed by people traveling at different speeds. Albert Einstein was only 26 years old, unknown outside small academic circles in Switzerland. Yet he had become fixated on a strange contradiction hidden inside physics itself. Light behaved too perfectly. Every experiment suggested the same impossible thing. No matter how fast an observer moved, light always arrived at exactly the same speed, not approximately, exactly 299,792,458 meters per second. The number never changed. This broke ordinary intuition completely. If you throw a ball forward from a moving train, the ball inherits the train's speed. Common sense says light should behave the same way, but it did not. A flashlight switched on aboard a moving train produced light traveling at the exact same speed as light emitted from a stationary lamp on Earth. Einstein accepted the measurement instead of resisting it. Everything else had to bend around that fact. His special theory of relativity, published in 1905, rebuilt physics from this single assumption. Space could no longer remain fixed. Time could no longer flow equally for everyone. Distance, duration, and simultaneity became flexible quantities, changing depending on motion and perspective. The consequences were severe. As an object accelerates, its energy increases, but near light speed, something extraordinary happens. More and more of that energy stops increasing velocity and instead warps the relationship between mass, time, and motion itself. Each additional push becomes less effective than the last. The mathematics climb toward infinity. To move a physical object with mass all the way to light speed would require infinite energy, not enormous energy, infinite. The universe appears constructed to prevent it entirely, but relativity carried stranger effects quietly inside it. Time dilation, the slowing of time for moving observers, was not philosophical speculation. It became measurable reality. Atomic clocks flown aboard aircraft returned ticking slightly differently than identical clocks left on Earth. Particles created in Earth's upper atmosphere survived longer when moving near light speed because time itself stretched for them during flight. The universe kept confirming Einstein again and again, and the scale of the problem became unbearable once we looked outward. Alpha Centauri, the nearest star system, sits roughly 4.37 light years away. Our fastest probes today move around 36,000 miles per hour. At that speed, crossing the distance would require roughly 78,000 years, longer than recorded human civilization. The Milky Way spans approximately 100,000 light years from edge to edge. Under relativity, the stars did not merely feel distant, they became functionally unreachable on human timescales. Physicists accepted this with remarkable confidence because the evidence never cracked. Every accelerator experiment, every satellite correction, every observation of high energy particles reinforced the same conclusion. The speed limit was real, which is exactly why the equations discovered decades later felt so unsettling. Long before the idea carried his name, Miguel Alcubierre spent his childhood in Mexico City, staring upward through polluted urban skies, trying to understand how the universe organized itself. He was born in 1964, decades after Einstein had already transformed physics into a world where relativity was treated less like speculation and more like bedrock. By 1994, Alcubierre was working at the University of Wales in Cardiff as a theoretical physicist. His field was general relativity, Einstein's larger gravitational framework, describing how mass and energy shape spacetime itself. The equations were notoriously difficult. Most physicists spent entire careers studying only fragments of their implications. But the question that pulled Alcubierre into history did not begin inside a laboratory. It began with television. He had been watching Star Trek, specifically the fictional warp drive that allowed ships to cross impossible distances between stars. Most scientists treated the concept as narrative convenience. Alcubierre approached it differently. Could such a mechanism exist without violating Einstein's equations? Not practically, mathematically. So he opened the field equations directly. General relativity describes gravity not as a force, but as geometry. Matter bends spacetime. Spacetime tells matter how to move. Planets orbit stars because they are following curves in the structure of reality itself. The equations contain no preferred shapes, only relationships between curvature, energy, motion, and distance. That flexibility mattered enormously. Alcubierre noticed something subtle hidden inside the mathematics. Einstein's speed limit applies to objects moving through spacetime locally, but the equations themselves never explicitly forbid spacetime from changing shape and carrying objects with it. The distinction was everything. If space ahead of a spacecraft could compress while space behind it expanded, the craft would effectively move enormous distances without ever accelerating through local space faster than light. Inside its immediate surroundings, the ship would remain stationary. The universe itself would do the moving. A simple analogy helps. Imagine standing motionless on a moving walkway inside an airport terminal. You are not walking unusually fast. The floor beneath you carries you forward. Alcubierre realized spacetime might function similarly if its geometry could somehow be manipulated. The ship becomes the still point. The bubble moves instead. In 1994, Alcubierre published a paper titled The Warp Drive: Hyperfast Travel Within General Relativity in the respected journal Classical and Quantum Gravity. This was not fringe speculation or science fiction fan theory. It was formal mathematical physics, peer reviewed and published within one of the field's legitimate academic journals. And something unusual happened. The physics community did not dismiss it. Researchers examined the equations carefully because the solution itself appeared internally consistent. The mathematics worked. No algebraic mistake collapsed the proposal. No direct contradiction with Einstein's equations emerged. Physicists disagreed about practicality immediately, especially regarding energy requirements, but the geometry itself survived scrutiny. The paper also introduced a new phrase into scientific literature, the Alcubierre metric. In relativity, a metric is a mathematical description of spacetime geometry. Alcubierre had not built a warp drive. He had done something stranger. He had shown that Einstein's universe contained room for one. Imagine a spacecraft suspended inside a perfectly calm region of spacetime, while the universe outside it bends and flows like a current around stone. Inside that region, a coffee cup rests normally on a table. A heartbeat keeps ordinary rhythm. A person standing in the corridor feels no crushing acceleration, no violent thrust, no sensation of motion at all. This stillness matters deeply. The Alcubierre solution does not treat the ship as the thing being accelerated. Instead, it surrounds the vessel with a controlled geometric distortion called a warp bubble, a region where spacetime remains flat and locally unchanged, while the surrounding universe shifts shape around it. The crew simply rides inside. Ahead of the bubble, spacetime compresses. Distances contract before the ship ever crosses them. The destination itself becomes nearer because the structure of space between 2 points shrinks. Behind the bubble, space-time expands outward, stretching away and carrying the bubble forward through the changing geometry. The motion belongs to space, not the vessel. This distinction protects the idea from directly violating special relativity. Einstein's speed limit governs objects moving through local space. It says nothing about how quickly space itself may expand, contract, or rearrange. The ship remains motionless relative to the tiny region immediately surrounding it at every moment of the journey. Locally, nothing breaks. From far away, everything changes. Alcubierre's original paper described a bubble approximately 100 meters across, large enough to contain a spacecraft and internal living space comfortably. Within that boundary, physical laws behave normally. Light moves normally. Clocks tick normally. Biological processes proceed normally. But outside the bubble, geometry becomes dynamic. The front edge compresses spacetime continuously, while the rear edge expands it. Together, these distortions create effective motion without local acceleration. The bubble can cross enormous distances, while the ship itself never outruns light within its own neighborhood of spacetime. The closest real analogy exists already in cosmology. Distant galaxies are currently receding from us faster than light because the universe itself expands between galaxies. This is not controversial. Astronomers observe it directly through redshift measurements, the stretching of light toward longer wavelengths as cosmic expansion carries galaxies farther apart. Nothing illegal occurs there either. The galaxies are not sprinting through space faster than light. Space between galaxies grows. Alcubierre recognized that general relativity already permits this category of motion naturally on cosmic scales. He simply localized it, and one consequence separates the warp bubble from nearly every earlier faster than light concept imagined in fiction or speculative physics. Inside the bubble, the crew experiences no relativistic time debt. Time dilation, the slowing of time during near light speed travel, does not accumulate for them relative to observers on Earth because locally they are never moving at relativistic speed through surrounding space. They age normally. A voyage lasting months for the crew lasts months for Earth as well. No frozen generations remain behind. No return to a distant future civilization unfolds automatically through the mechanics of the trip itself. The bubble changes geometry without forcing the travelers to outrun time. There is a number hidden inside modern cosmology that feels impossible the first time you hear it. The observable universe spans roughly 93 billion light years across. Yet the universe itself is only about 13.8 billion years old. At first glance, the math fails completely. How can light from regions 93 billion light years apart have reached us if not enough time has existed for that journey? Even moving at light speed continuously since the beginning of time would not seem sufficient, but the contradiction dissolves once we stop imagining space as static. The universe is not expanding into emptiness like smoke entering a room. Space itself stretches internally. Every enormous gulf between galaxies slowly widens because the fabric separating them grows over time. Galaxies are not necessarily racing outward through space like debris from an explosion. The stage itself is enlarging. This expansion was first measured in the 1920s by astronomer Edwin Hubble. Using redshift observations, the stretching of light toward longer wavelengths, Hubble discovered that distant galaxies systematically move away from us. More importantly, the farther a galaxy sits from Earth, the faster it appears to recede. The relationship became known as the Hubble constant. Today, its value is estimated near 70 kilometers per second per megaparsec. A megaparsec equals roughly 3.26 million light years. That means every additional megaparsec of distance adds another 70 kilometers per second of recessional velocity caused purely by expanding space. The effect compounds endlessly. Far enough away, galaxies recede faster than light itself. This is not theoretical interpretation or speculative philosophy. Astronomers observe it directly across enormous cosmic distances. Beyond approximately 14 billion light years, we cross what cosmologists call the Hubble horizon, the boundary where expansion outpaces light's ability to ever bridge the gap back toward us. Those regions become unreachable forever. Even photons lose the race. But the deeper revelation lies earlier in cosmic history. Shortly after the Big Bang, during an interval unimaginably brief, the universe underwent cosmic inflation, a runaway expansion event occurring within less than a trillionth of a second. During that moment, space-time expanded by at least a factor of 10, raised to the 26th power. Faster than light, far faster, and yet relativity remained intact because nothing traveled locally through space beyond Einstein's limit. Space itself expanded, the geometry changed, distances inflated almost instantly between neighboring regions of the young universe. We still see the aftermath tonight, the cosmic microwave background, faint microwave radiation filling all directions of space, preserves the cooled afterglow of that primordial era. Satellites such as Planck mapped these ancient temperature fluctuations with extraordinary precision, revealing patterns that align almost perfectly with inflationary cosmology. The evidence surrounds us constantly. This changes the emotional weight of Alcubierre's proposal entirely. He was not inventing a fictional loophole disconnected from observed reality. The mechanism already exists naturally on the largest scales known to science. The universe has operated this way since its beginning. Alcubierre simply recognized the pattern hidden inside Einstein's equations and asked whether a civilization might someday learn to shape a smaller version deliberately. For a brief moment after Alcubierre's paper appeared, the equations seemed almost unnervingly elegant. The geometry worked. Relativity remained intact. Space itself could, at least mathematically, carry a spacecraft across impossible distances without locally breaking Einstein's limit. Then, physicists calculated the energy bill. The optimism collapsed quickly. Alcubierre's original 1994 model described a warp bubble roughly 100 meters wide, moving effectively at light speed. To generate the required spacetime curvature, the equations demanded an amount of energy comparable to converting the entire mass of Jupiter directly into usable fuel through Einstein's mass-energy relationship, E equals mc squared. Jupiter is not small. Its mass equals approximately 1.898 octillion kilograms, more than 318 times the mass of Earth. Even writing the number strains intuition because nothing in ordinary human experience approaches that scale physically or energetically, but the energy estimate became stranger still. Human civilization currently consumes roughly 580 quintillion joules of energy annually across every nation, city, aircraft, factory, power plant, and digital network combined. Alcubierre's warp geometry required something closer to 10 raised to the 64th joules. The gap bordered on absurdity. It was less like comparing a candle to the sun and more like comparing a single grain of dust to an entire galaxy. Most physicists looked at the estimate and quietly concluded the discussion had ended before it truly began. But another problem emerged beneath the numbers themselves. The required energy was not merely enormous, it possessed the wrong sign. The equations demanded negative energy density, a condition where energy behaves gravitationally opposite to normal matter. Instead of pulling inward through gravity the way planets, stars, and gas clouds do, this form of energy would push outward against space-time itself. Physicists called it exotic matter. The term sounds dramatic, but it refers to a precise property. Matter with negative energy density violates classical expectations about how mass and energy should behave under gravity. No laboratory had ever produced it in usable quantities. No industrial process even hinted at scalability. Yet, quantum physics complicated the situation immediately. A known phenomenon called the Casimir effect already demonstrated tiny amounts of negative energy behavior experimentally. First predicted in 1948 by Dutch physicist Hendrik Casimir, the effect occurs when two conductive metal plates are positioned extraordinarily close together, separated by distances measured in nanometers. At that scale, quantum vacuum fluctuations become uneven. The vacuum between the plates contains fewer allowable quantum states than the vacuum outside them, creating measurable pressure differences. The plates move together slightly as the surrounding vacuum effectively pushes inward harder than the vacuum trapped between them. Negative energy appears indirectly in the mathematics, describing that pressure imbalance. Real measurements confirmed it, but the quantities involved were microscopic beyond imagination. The Casimir effect produces forces detectable only with highly sensitive instruments under carefully controlled laboratory conditions. Scaling that phenomenon upward to planetary energy regimes remained completely beyond known engineering. So the verdict of the 1990s settled into an uneasy middle ground. The warp drive appeared mathematically consistent within general relativity. No immediate physical law forbade it outright. But nature demanded prices no civilization knew how to pay. Most scientific ideas disappear quietly once the numbers become catastrophic. Papers stop circulating. Funding dries up. Researchers move toward problems that appear survivable within a human lifetime. But a few physicists kept returning to the warp equations anyway. One of them was Harold White, often called Sunny White, an engineer and physicist working at NASA's Johnson Space Center during the early 2000s. White approached the problem from an unusual angle. He did not assume Alcubierre's energy estimates were permanent features of the theory. He questioned the shape instead. Alcubierre's original proposal described a smooth spherical warp bubble surrounding a spacecraft. White wondered whether altering the bubble's geometry could dramatically change the energy requirements while preserving the core relativistic framework. General relativity allows that possibility. In Einstein's equations, geometry and energy remain deeply connected. Change the curvature pattern, and the energetic demands can shift with it. White proposed a toroidal structure, donut-shaped rather than spherical, combined with oscillating field intensities instead of a perfectly static warp region. The mathematical consequences were startling. According to White's revised calculations, the required exotic matter dropped from something comparable to Jupiter's mass energy down to roughly 700 kilograms, about the mass of a small car. The energy requirements remained far beyond anything humanity could produce, but psychologically, the proposal entered a different category entirely. Not impossible, only unreachable. White published the work in 2011 and presented it publicly at the 100-Year Starship Symposium, a DARPA and NASA-supported initiative focused on serious, long-term interstellar research. The atmosphere surrounding the presentation remained careful and restrained. No one believed a warp engine was suddenly close. But the equations had survived another challenge. The wider physics community reacted cautiously. Many researchers accepted White's mathematics as internally consistent, while remaining skeptical about the unresolved exotic matter problem. Reducing the energy requirements did not remove the need for negative energy density. The fundamental obstacle still stood directly in front of the concept. Yet, something important had changed. Warp drive research had moved beyond pure speculation. White helped establish the Advanced Propulsion Physics Laboratory at Johnson Space Center, better known by its nickname, EagleWorks. The laboratory received actual NASA funding to investigate tiny spacetime distortion effects experimentally rather than philosophically. Inside EagleWorks, researchers used a modified Michelson interferometer, an instrument capable of detecting unbelievably small changes in distance by splitting and recombining laser beams. Interferometry measures disruptions far smaller than the width of a proton, making it one of the most sensitive measurement techniques ever developed. The laboratory searched for microscopic spacetime distortions generated by carefully engineered electromagnetic systems. The expected effects were tiny, buried beneath vibration, thermal drift, and environmental interference, most likely too small to detect. But the shift mattered. Scientists were now constructing instruments, running experiments, calibrating lasers, and testing whether spacetime itself could be manipulated at tabletop scales. The warp drive had crossed an invisible boundary between theoretical curiosity and experimental physics. The phrase exotic matter sounds like something hidden inside a classified laboratory or buried beneath a science fiction screenplay. But the idea emerged from a much quieter place, from physicists trying to understand what empty space actually contains. An empty space turned out not to be empty at all. Before we can understand negative energy, we need to separate it from another concept people often confuse with it: antimatter. The two sound related. They are not. Antimatter behaves almost exactly like ordinary matter, except with opposite electric charge. A positron, for example, carries the same mass as an electron, but positive charge instead of negative. When antimatter meets normal matter, both annihilate and release enormous energy. But antimatter still obeys gravity normally. It falls downward. It possesses positive mass and positive energy. In every tested gravitational experiment so far, antimatter behaves like ordinary physical substance, moving through the same spacetime geometry as everything else. Exotic matter would behave differently. Matter with negative energy density would respond to gravity oppositely. Instead of attracting surrounding matter inward, it would create repulsive gravitational effects, pushing outward against space-time curvature itself. In principle, this outward pressure is what makes the warp bubble mathematically possible. The theoretical basis comes from quantum field theory, our framework for describing particles and forces at microscopic scales. According to quantum mechanics, even a perfect vacuum cannot remain completely still. Uncertainty is built into reality. Fundamentally, fields fluctuate continuously. Virtual particles appear and disappear constantly. These are temporary quantum disturbances, fleeting pairs of particles emerging from the vacuum and annihilating almost immediately. Space, at the smallest scales, behaves less like emptiness and more like restless activity hidden beneath stillness. The Casimir effect became one of the first measurable hints that this vacuum activity was physically real. In 1948, Dutch physicist Hendrik Casimir predicted that two uncharged metal plates, placed extremely close together, would experience a tiny attractive force generated by altered quantum fluctuations between them. Nearly 50 years later, in 1997, physicist Steve Lamoro measured the effect experimentally with high precision. The force existed exactly where theory predicted. Between the plates, certain vacuum fluctuations become suppressed because only specific wavelengths fit inside the narrow gap. Outside the plates, the vacuum fluctuates more freely. The imbalance creates measurable pressure differences associated mathematically with negative vacuum energy density. But the quantities involved remain microscopic. The Casimir effect produces roughly 1,000th of a joule per cubic meter under laboratory conditions. A functional warp geometry would require vastly larger concentrations, sustained across enormous spatial regions. No known process can scale the phenomenon remotely close to those requirements, and additional restrictions emerged during the 1990s. Physicists Lawrence Ford and Thomas Roman developed what became known as quantum inequalities, mathematical constraints limiting how large and long-lasting negative energy concentrations may become. The universe appeared willing to tolerate tiny violations briefly and locally, but resistant to stable macroscopic reservoirs. Yet the equations stopped short of prohibition. Ford and Roman constrained geometry rather than possibility itself. Their work suggested that arrangement, distribution, and timing mattered critically, which is precisely why researchers like Harold White focused so intensely on reshaping the warp bubble rather than abandoning it altogether. By the early 2020s, warp drive research occupied an uneasy position inside physics. The equations continued surviving scrutiny, yet the dependence on exotic matter kept the idea suspended beyond practical reach. Many researchers treated the subject cautiously, almost like a mathematical curiosity balanced at the edge of legitimacy. Then, in September of 2021, a paper appeared that shifted the discussion unexpectedly. It was titled Introducing Physical Warp Drives. The paper was published in Classical and Quantum Gravity by Alexei Bobrik and Gianni Martir, researchers working with the company Applied Physics. Their goal was not to promote faster than light travel directly. Instead, they approached the entire subject systematically, treating warp geometries less like speculative fantasy and more like a classification problem inside general relativity. They asked a different question entirely. What kinds of warp bubbles are actually allowed by known physics? To answer it, Bobrick and Martyr examined broad categories of space-time geometries rather than focusing narrowly on Alcubierre's original solution. They mapped how different curvature structures behave under Einstein's equations while testing whether those structures obey established energy conditions, the mathematical rules normally expected of realistic matter. The results divided the field cleanly. They discovered entire classes of warp configurations that required only positive energy density, meaning ordinary matter rather than exotic negative energy. For the first time, researchers demonstrated mathematically that warp bubble geometries themselves do not inherently demand impossible forms of matter. That distinction mattered enormously. But there was an important limitation. These newly identified designs could not exceed light speed. They produced sublight warp effects only, space-time distortions capable of moving a region of space without violating known energy conditions, yet insufficient for true faster-than-light travel. Still, the implications reached far beyond velocity. The paper introduced the term physical warp drive, meaning a warp metric compatible with all currently accepted energy constraints using realistic matter sources. The underlying mechanism of spacetime engineering had crossed a conceptual threshold. Warp bubbles were no longer automatically tied to impossible negative energy reservoirs. The geometry itself survived independently. Around the same period, physicist Erich Lentz at the University of Göttingen developed a separate approach, arriving at surprisingly similar territory. Lentz explored structures called solitons, self-reinforcing wave formations capable of maintaining stable shapes while propagating through a medium. Ocean waves sometimes behave this way. So can electromagnetic systems. Lentz derived warp bubble solutions built from carefully arranged soliton configurations that also avoided exotic matter entirely. His energy requirements remained immense, still far beyond any achievable technology, but the mathematical barrier surrounding negative energy had weakened significantly. Not removed completely, but narrowed. The field now separated into two distinct branches. Faster-than-light warp drives still appeared to require exotic matter and all the unresolved problems attached to it. Yet slower-than-light space-time manipulation no longer depended on impossible physics necessarily. That changed the emotional atmosphere surrounding the research. For decades, critics argued the warp bubble concept failed because exotic matter itself might not exist meaningfully at usable scales. After 2021, that argument became less certain. The conversation shifted away from whether space-time engineering was fundamentally forbidden and toward how much control over geometry nature might eventually permit. There is a deeper reason physicists become uneasy around faster-than-light travel. It is not primarily the energy requirements, though those remain enormous. It is not even exotic matter. Beneath all of those difficulties sits something stranger. Time itself begins to misbehave. Einstein's special relativity reshaped space and time into a single connected structure called spacetime. Different observers moving relative to one another do not agree perfectly on durations, distances, or even the order of events. Usually these disagreements remain small and harmless at ordinary speeds. But near light speed, the disagreements grow severe. Beyond light speed, they become dangerous. The mathematics responsible are called the Lorentz transformations, equations describing how measurements change between moving reference frames. A reference frame simply means a particular observer's perspective through spacetime. According to those transformations, if information or objects travel faster than light in one frame, another observer moving differently can measure the same event sequence occurring backward in time. Not metaphorically, literally backward. This leads to one of the strangest thought experiments in modern physics, the tachyonic antitelephone. Tachyons are hypothetical particles that always move faster than light. Physicists discovered mathematically that if faster than light communication exists, two observers moving relative to one another could exchange messages in such a way that a reply arrives before the original message was sent. Cause follows effect backward. The loop closes on itself. This creates what physicists call a closed causal loop, a sequence where events become self-contradictory. A person could theoretically receive information from their own future before deciding whether to send it. Logic begins collapsing under the geometry itself. Stephen Hawking took this problem seriously enough to propose the chronology protection conjecture in 1992. The name sounds almost poetic, but the idea was brutally practical. Hawking suspected the laws of physics contain hidden mechanisms preventing time paradoxes from ever becoming physically realizable. Reality protects chronology automatically. According to Hawking's argument, quantum effects near any forming time machine or closed time-like curve, a path through spacetime returning to its own past, would generate runaway energy densities strong enough to destroy the structure before paradoxes could emerge. The universe may sabotage time travel preemptively. Warp bubbles inherit this concern naturally. If a spacecraft crosses interstellar distances effectively faster than light, then under certain relativistic reference frames, an outside observer could calculate the arrival occurring before departure. The ship's crew might experience perfectly ordinary forward time progression internally, while external geometry produces reversed causal ordering elsewhere. This is where the discussion becomes genuinely unsettled. Warp metrics do not automatically guarantee practical time travel. The equations become extraordinarily sensitive once relativistic geometry, quantum effects, and reference frame transformations interact simultaneously. Physicists do not yet possess a complete theory, unifying gravity with quantum mechanics strongly enough to analyze these conditions conclusively. The causal structure remains unresolved. That uncertainty matters. Causality, the principle that causes precede effects, forms one of the deepest assumptions underlying all physics. If faster than light systems destabilize causality fundamentally, then nature may forbid them through mechanisms we do not yet understand. But the problem extends beyond warp drives specifically. Any mechanism allowing effective, faster than light travel inherits similar paradoxes automatically. The issue belongs not to Alcubierre's equations alone, but to the structure of spacetime itself once light speed ceases functioning as an absolute boundary. A spacecraft drifting inside a warp bubble appears, at first glance, strangely peaceful. No violent acceleration presses against the hull. No relativistic distortions twist the crew's clocks. The interior remains locally calm while spacetime bends beyond its boundary. But hidden inside that calmness sits another problem. The crew may not actually be able to control the bubble once it forms. This difficulty emerged only after physicists studied Alcubierre's geometry more carefully in the years following the original paper. The issue was subtle enough to escape immediate attention because it did not concern energy, propulsion, or stability directly. It concerned communication. To alter a warp bubble during flight, signals from the spacecraft would need to reach the bubble walls controlling the surrounding spacetime geometry. That sounds simple under ordinary conditions. Light signals travel outward. Computers issue commands. Systems respond. Inside a warp geometry, things become stranger. The leading edge of the bubble effectively moves at or beyond light speed relative to external spacetime. Because no information can locally outrun light, signals generated inside the bubble cannot catch up to the front boundary, controlling the contraction region ahead. The crew becomes causally disconnected from the forward wall. Causally disconnected means information physically cannot cross the separation under known relativistic rules. The boundary outruns the signals attempting to reach it. Once the bubble activates, the spacecraft may lose the ability to steer, slow down, reshape the geometry, or terminate the field from within. The ship becomes a passenger, not a pilot. This transforms the engineering picture dramatically. A warp drive begins resembling infrastructure rather than a self-contained vehicle. The bubble might need to be programmed entirely before departure, with trajectories and deceleration points embedded into the geometry from the beginning. Some physicists proposed external control systems instead. A destination civilization, for example, could theoretically manipulate the receiving end of a warp trajectory remotely, guiding arriving bubbles toward stable deceleration zones. Another possibility involves pre-existing networks distributed through interstellar space, more comparable to rails or corridors than independent rockets. The analogy shifts completely. Researchers naturally explored whether quantum entanglement could bypass the communication barrier. Entanglement links particles through correlated quantum states, regardless of separation distance. Einstein famously called it spooky action at a distance because measurements performed on one particle instantly influence statistical properties of the other. But entanglement carries severe limitations. The no communication theorem, a formal result in quantum mechanics, prevents entanglement from transmitting usable information faster than light. Correlations appear instantly, yet controllable messages do not. The universe preserves causality carefully, even within its strangest quantum behaviors. So, entanglement offered no clean escape. Another proposal approached the issue geometrically instead of communicationally. Rather than steering actively during travel, the bubble could contain variable internal structures pre-configured to collapse or decelerate automatically upon reaching specific space-time coordinates, like a timed sequence or a gravitational trajectory calculated years beforehand. This does not solve every difficulty, but it reframes the entire concept fundamentally. A warp drive may never behave like fictional spacecraft weaving freely between stars under direct human control. The horizon problem suggests something slower operationally, more rigid, more infrastructural, less like an aircraft, more like a railway built through space-time itself. Inside a laboratory at NASA's Johnson Space Center, the search for space-time manipulation became unexpectedly physical, not dramatic, not cinematic. There were no glowing engines or suspended spacecraft prototypes waiting beneath tarps. Only instruments, cables, lasers, vacuum equipment, noise isolation systems. Beginning around 2012, Harold White's EagleWorks laboratory attempted something extraordinarily difficult, creating and detecting microscopic space-time distortions at tabletop scale. The goal was modest compared to fictional warp drives. No one expected faster-than-light travel to emerge from the experiments directly. They were searching for traces. The central setup involved a ring-shaped capacitor charged with high voltage. A capacitor stores electrical energy between conductive surfaces. White's team hypothesized that carefully configured electromagnetic fields might produce minute geometric distortions within spacetime itself, incredibly tiny deviations, impossible to notice directly but potentially measurable, with precise optical instruments. The detection system mattered more than the field source. Eagleworks relied on a modified Michelson interferometer, a device originally invented during the 19th century and later refined into one of the most sensitive scientific instruments ever built. Interferometers work by splitting laser light into separate paths, then recombining the beams afterward. If space-time shifts even slightly along one path, the returning light waves interfere differently. Tiny distortions become visible as changing interference patterns. The same principle underlies LIGO, the Laser Interferometer Gravitational Wave Observatory that detected gravitational waves from merging black holes in 2015. Eagleworks scaled that general approach down dramatically into laboratory dimensions, attempting to detect disturbances vastly smaller than atomic structures. The expected signals were microscopic beyond ordinary intuition. In 2013, White reported anomalous readings during some experimental runs. The interference patterns shifted slightly in ways that could, under certain interpretations, align with minute spacetime distortions produced by the apparatus itself. But the results remained deeply uncertain. The broader physics community responded with heavy skepticism because the measured deviations sat extremely close to environmental noise levels. Thermal expansion from heat fluctuations, microscopic vibrations from nearby equipment, electromagnetic interference, or subtle calibration errors could potentially produce similar signals. Nothing definitive emerged. Importantly, NASA never announced a breakthrough. White himself described the findings cautiously, emphasizing their preliminary and inconclusive nature rather than presenting them as proof of warp physics. No verified space-time engineering event had occurred inside the laboratory, and independent replication never followed. Other research groups failed to reproduce the reported effects reliably at comparable scales, leaving the original measurements unresolved rather than confirmed. Over time, Eagleworks gradually lost prominence as a primary NASA initiative, though White continued publishing theoretical work and discussing propulsion concepts publicly afterward. Yet the laboratory still altered the field in one important way. Before Eagleworks, warp drive discussions existed mostly within equations and theoretical papers. After Eagleworks, researchers possessed at least a tentative experimental framework for investigating microscopic spacetime phenomena directly through interferometric measurement techniques. The lab established methodology. That matters in physics. Many major discoveries begin not with clear signals, but with instruments sensitive enough to ask meaningful questions for the first time. Eagleworks did not prove warp drives exist. It proved scientists could build systems specifically designed to search for tiny geometric effects inside spacetime itself. The distinction is subtle, but scientifically, it is enormous. At the smallest scales, we can describe mathematically, space does not behave like emptiness. Even in total darkness, with all particles removed and every known field minimized, the vacuum continues fluctuating beneath apparent stillness. Physics calls this zero-point energy. The term refers to the lowest possible energy state of a quantum system, but lowest does not mean zero. Quantum uncertainty prevents particles and fields from becoming perfectly motionless. Tiny fluctuations remain unavoidable because nature forbids absolute stillness at microscopic scales. The vacuum never fully settles. This has strange implications. Quantum field theory predicts that empty space contains immense background energy woven into spacetime itself. Calculations vary dramatically depending on the methods used, but some estimates produce vacuum energy densities vastly exceeding anything observed in stars, galaxies, or ordinary matter. Most of that energy appears inaccessible, perhaps permanently. Yet the existence of the vacuum reservoir inspired another branch of speculative propulsion research running parallel to warp drive discussions. Instead of bending space-time directly, some physicists and engineers explored whether propulsion systems might interact with the quantum vacuum itself, extracting momentum or thrust from underlying field fluctuations. One controversial example became briefly famous. In the early 2000s, engineer Roger Shawyer proposed the M drive, a microwave cavity thruster supposedly capable of generating propulsion without expelling propellant. The design used resonant microwave radiation trapped inside an asymmetrical chamber. According to Shawyer, internal electromagnetic interactions could produce net thrust despite violating ordinary conservation expectations. The claims triggered immediate skepticism. They also triggered experiments. Multiple laboratories tested versions of the device over the following years, including teams connected to NASA EagleWorks. Some measurements appeared to detect tiny thrust signals, small enough to remain ambiguous but persistent enough to keep discussion alive temporarily. The possibility attracted attention because propellantless propulsion would revolutionize spaceflight even without faster than light capability. But the evidence weakened steadily. In 2021, researchers at Dresden University in Germany performed carefully controlled tests examining the M drive under improved shielding conditions. Their analysis showed the apparent thrust effects matched interference generated by Earth's magnetic field, interacting with electrical currents inside the apparatus. Once properly isolated, the thrust disappeared. The consensus shifted rapidly afterward. Most physicists now regard the M drive as almost certainly non-functional as a real propulsion mechanism. But the episode still revealed something important about the scientific process. Researchers were willing to test impossible sounding ideas experimentally, carefully, publicly, repeatedly. Other concepts remain more speculative still. Quantum vacuum plasma thrusters, for example, explore whether vacuum fluctuations or quantum field interactions could influence charged plasma flows in unconventional ways. These systems remain theoretical, with no verified experimental demonstrations yet approaching practical propulsion. But the connection to warp research persists quietly beneath the surface. If the quantum vacuum truly contains enormous latent energy, then future physics might eventually discover methods for engineering localized vacuum states directly. Exotic matter, negative energy density, and spacetime curvature all intersect conceptually within quantum field behavior at extremely small scales. No established mechanism exists today. Still, warp drive research no longer sits entirely isolated from mainstream theoretical physics. Questions about vacuum structure, quantum fields, and space-time geometry already occupy active areas of cosmology and particle theory. The speculative edge appears not in asking whether the vacuum matters physically. It clearly does. The uncertainty lies in whether intelligence can ever learn to shape those fluctuations deliberately enough to matter technologically. Einstein's field equations do not read like laws carved into stone tablets. They are not a catalog of approved phenomena or forbidden technologies. They are mathematical relationships connecting matter, energy, motion, and the curvature of spacetime itself. The equations describe geometry. What emerges from that geometry depends entirely on the solutions hidden inside it. Some solutions correspond closely to the universe we observe every night. Others describe conditions so strange they feel detached from physical reality entirely. Yet, mathematically, the equations permit them all, unless additional constraints are imposed afterward. That flexibility unsettled even Einstein himself. Over the past century, physicists discovered many exotic solutions buried inside general relativity. Schwarzschild black holes emerged first, describing non rotating gravitational collapses so extreme that escape becomes impossible beyond the event horizon. Later came Kerr black holes, rotating versions where spacetime itself drags around the singularity like water spiraling toward a drain. Then came stranger geometries. Einstein-Rosen bridges, commonly called wormholes, connected distant regions of spacetime through hypothetical tunnels. Closed time-like curves described paths looping backward through time. And eventually, the Alcubierre metric appeared among them, a mathematically valid warp geometry capable of effective faster-than-light travel under certain conditions. But perhaps the most disturbing example arrived in 1949. Mathematician Kurt Gödel, famous for proving deep limitations within formal logic systems, discovered an exact solution to Einstein's equations, describing a rotating universe where closed time-like curves exist everywhere, naturally. In Gödel's universe, any observer could theoretically travel into their own past simply by following particular paths through spacetime. Time travel emerged directly from Einstein's equations, not from fiction. Einstein found the result deeply troubling because he believed causality should remain protected fundamentally. Gödel's solution suggested the equations themselves possessed fewer safeguards than their creator expected. Mathematics allowed structures Einstein felt physical reality ought to reject. Physicists responded by introducing additional assumptions called energy conditions. These conditions function like filters, restricting which solutions correspond to realistic matter distributions. Four became especially important: the weak, strong, dominant, and null energy conditions. Each imposes different requirements on how energy and momentum behave gravitationally. The weak energy condition matters most here. It states that any observer moving through spacetime should measure non-negative local energy density. Ordinary matter satisfies this naturally. Stars, planets, gas clouds, radiation, and living organisms all obey it without difficulty. The Alcubierre metric does not. Warp geometries require regions of negative energy density, violating the weak energy condition directly. For many physicists, this violation became the primary reason to doubt practical warp drives, despite the equations themselves remaining internally consistent. But quantum mechanics complicated the picture once again. Phenomena like the Casimir effect already produced tiny, transient violations of the weak energy condition experimentally. Vacuum fluctuations, under carefully arranged conditions, generate localized, negative energy densities measurable in laboratory systems. The violations remain microscopic and temporary, yet they exist physically. Nature bends the rule occasionally. That distinction matters enormously because it shifts the location of the problem. General relativity does not forbid the Alcubierre metric mathematically. The equations permit the geometry cleanly. The obstacle emerges from our current understanding of matter, energy, and quantum constraints at usable scales. The prohibition belongs to physics we have not fully unified yet, not to Einstein's gravitational framework itself. The misunderstanding begins with a sentence repeated so often it starts sounding absolute. Nothing can move faster than light. Most people hear that and imagine a universal prohibition applying equally everywhere under all circumstances. But relativity says something more precise. The speed of light, 299,792,458 meters per second, governs how fast matter or information can move locally through spacetime at any given point. It is a local constraint woven into the geometry surrounding an observer. Local is the important word. The equations do not place the same restriction on spacetime itself. This distinction already appears inside observational cosmology. We can see it directly in the oldest light filling the universe, the cosmic microwave background. That radiation emerged roughly 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely for the first time. The glow still surrounds us tonight. Satellites such as Planck mapped this background radiation across the entire sky with extraordinary precision. The measurements revealed something deeply strange. Regions of the early universe, now separated by enormous distances, possess nearly identical temperatures, despite being too far apart for light to have traveled between them under ordinary expansion rates. They should not match so closely. This discrepancy became known as the horizon problem. In cosmology, a horizon marks the maximum distance over which causal interaction could have occurred since the beginning of the universe. The observed uniformity of the microwave background suggested distant regions somehow equilibrated before separating. Something dramatic had happened early on. The leading explanation is inflation theory, proposed by physicist Alan Guth in 1980. According to inflationary cosmology, the infant universe underwent a phase of exponential expansion less than a fraction of a second after the Big Bang. During approximately 10 raised to the negative 32nd seconds, spacetime expanded by at least a factor of 10 raised to the 26th power, far beyond light speed. Yet relativity remained intact because matter was not outrunning light locally through surrounding space. Space itself expanded. Distances inflated faster than light could cross them. The geometry changed globally. Inflation is not considered fringe physics today. It became the dominant cosmological framework because it explains several otherwise puzzling observations simultaneously, including the flatness of the universe, the near isotropy of the microwave background, and the distribution of primordial density fluctuations from which galaxies eventually formed. The proposed mechanism involved a scalar field called the inflaton, a hypothetical energy field driving repulsive gravitational behavior during the universe's earliest moments. Instead of pulling matter inward through gravity, the inflaton generated explosive expansion of spacetime itself. This matters enormously for warp drive discussions. Alcubierre's proposal does not ask physics for a phenomenon completely absent from nature. The universe already demonstrated faster than light expansion through spacetime geometry during inflation. Cosmology accepts that history because the evidence supporting it appears written across the microwave background itself. The challenge is scale and control. Inflation operated across the infant cosmos under conditions far beyond human engineering. A warp bubble attempts something radically smaller, localized manipulation of space-time geometry performed intentionally around a spacecraft. But the category of phenomenon remains familiar to modern cosmology. The universe has already shown spacetime can expand faster than light. On clear nights, the nearest star beyond our sun already hangs above us invisibly. Proxima Centauri is too faint for unaided human eyes, buried within the glare of the larger Alpha Centauri system, roughly 4.243 light-years away. Cosmically, that distance is tiny. Humanly, it is almost unbearable. In 2016, astronomers confirmed the discovery of Proxima Centauri b, an exoplanet orbiting within the star's habitable zone, the region where temperatures may allow liquid water to exist on a planetary surface. The planet appears roughly Earth-sized and completes one orbit every 11.2 days around its dim red host star. A second world sits nearby tonight, yet reaching it remains another matter entirely. Voyager 1, the fastest spacecraft humanity has ever launched outward permanently, currently travels around 38,000 miles per hour relative to the Sun. At that speed, crossing the distance to Proxima Centauri would require approximately 73,000 years, longer than recorded civilization. Entire languages would emerge and vanish before arrival. Even ambitious modern concepts remain sobering. The Breakthrough Starshot initiative proposes accelerating ultralight spacecraft using giant Earth-based laser arrays, pushing reflective light sails toward approximately 10% of light speed. At that velocity, the journey to Proxima would still require roughly 42 years one way. And there is another problem. Those probes could not realistically slow down upon arrival. They would race through the target system at enormous speed, gathering data during a brief flyby before disappearing permanently into interstellar darkness. Light speed itself changes the scale dramatically. A spacecraft somehow capable of moving exactly at light speed could reach Proxima Centauri in 4.243 years from Earth's perspective. For the first time, interstellar travel begins fitting inside a single human lifetime operationally. But warp travel alters the picture even more profoundly. A functioning warp system capable of effective motion at 10 times light speed could cross the same distance in roughly 5 months each way. Suddenly, the nearest stars stop behaving like unreachable abstractions and begin resembling difficult but conceivable destinations. The reachable neighborhood expands quickly afterward. The TRAPPIST-1 system, located about 39 light-years away, contains 7 known rocky planets, including at least 3 potentially habitable worlds. At 10 times light speed, travel there would require roughly 1.4 years each direction. Not easy, but survivable within a mission framework. Kepler 452 b, sometimes called Earth's cousin because of its Earth-like orbital characteristics, lies approximately 1,400 light-years away. Even at 10 times light speed, the journey remains generational, around 140 years. Warp travel does not erase distance completely. The galaxy stays vast. But the implications remain extraordinary because the threshold changes fundamentally. Without faster-than-light capability, humanity remains effectively trapped inside its own stellar system indefinitely. Even nearby stars become separated by timescales hostile to biology, culture, and continuity. With even modest warp capability, dozens of nearby systems enter human reach within ordinary lifetimes. That changes the emotional architecture of the cosmos itself. The stars stop functioning purely as observation targets. They become places, possible destinations, potential neighbors. The difference is not merely technological. It is the difference between permanent isolation and the beginning of genuine contact with the wider universe surrounding us. In the summer of 1950, physicist Enrico Fermi sat at lunch with colleagues discussing extraterrestrial life when he asked a question so simple it became haunting. Where is everybody? The question later became known as the Fermi Paradox. A paradox forms when observations conflict sharply with expectation. In this case, the contradiction emerges from the sheer scale and age of the galaxy itself. The Milky Way is approximately 13.6 billion years old. Human technological civilization, by contrast, is almost unimaginably recent. Radio transmissions have leaked into space for barely more than 1 century. Industrial civilization occupies a time span thinner than dust against galactic history. If intelligent life emerges even rarely, then older civilizations should exist. Many of them. Even conservative models produce uncomfortable timelines. Imagine a civilization expanding outward slowly at only 1% of light speed, far below anything resembling warp travel. That pace already sounds enormous by human standards, yet cosmically it remains modest. At those velocities, a civilization could spread across the Milky Way in roughly 10 million years. 10 million years feels immense to us. But relative to the age of the galaxy, it is almost nothing, roughly 0.07% of galactic history. A civilization beginning expansion billions of years ago should have had time not merely to visit nearby stars, but to saturate the entire galaxy repeatedly. Yet, we see no evidence. No probes, no megastructures, no engineered galaxies glowing unnaturally in infrared surveys, no unmistakable signals crossing the radio sky. The silence itself becomes the observation requiring explanation. And warp travel intensifies the paradox dramatically. If faster than light movement proves physically achievable, then the colonization timescale collapses from millions of years into thousands or tens of thousands at most. Galactic distances cease functioning as meaningful barriers. Civilizations could spread, communicate, and interact across enormous regions rapidly enough to reshape stellar neighborhoods within comparatively brief cosmic intervals. The silence becomes louder, not quieter, because then another question emerges naturally. If space-time engineering sits within the laws of physics, why has no civilization's presence reached us unmistakably already? Why does Earth still appear observationally isolated inside a galaxy old enough to have produced technological societies billions of years before humanity existed? Several possibilities follow. None are comforting. Perhaps intelligent life is extraordinarily rare and humanity genuinely stands alone. Perhaps civilizations repeatedly destroy themselves before reaching interstellar capability through war, ecological collapse, artificial intelligence, or technological instability. Perhaps warp travel or advanced expansion introduces dangers, causing civilizations to disappear rapidly after achieving it. But another possibility unsettles people differently. Civilizations may already exist nearby while deliberately remaining hidden. In a universe where fast interstellar travel becomes possible, concealment itself gains strategic value. A civilization capable of manipulating space-time would also possess technologies far beyond human detection capabilities potentially. Silence may not indicate absence, it may indicate restraint or observation. The warp drive does not resolve the Fermi paradox. It sharpens every edge surrounding it. Because once faster than light travel enters the category of physical possibility, the galaxy begins looking less empty and more strangely quiet. And quietness at that scale becomes difficult to interpret benignly. Long before warp bubbles entered physics literature, another path through spacetime had already appeared quietly inside Einstein's equations. It did not bend space around a ship or compress distances dynamically. Instead, it connected distant regions directly, a tunnel through geometry itself. Physicists later called these structures wormholes, though the formal name is Einstein-Rosen bridges. The idea first emerged in 1935 when Albert Einstein and Nathan Rosen examined the Schwarzschild black hole solution within General Relativity. Initially, they were not searching for transportation systems. The bridge appeared mathematically as a peculiar feature attached to black hole geometry, a connection linking separate regions of spacetime through an internal throat, but the original structure proved unstable. Any attempt to cross it caused the passage to collapse too quickly for matter or information to survive transit. For decades, wormholes remained mostly mathematical curiosities. Then, science fiction unexpectedly influenced serious physics. In the late 1980s, astronomer Carl Sagan was writing the novel Contact and wanted an interstellar travel mechanism more scientifically grounded than ordinary, faster than light engines. He approached physicist Kip Thorne at the California Institute of Technology, asking whether anything inside general relativity might permit rapid travel between stars plausibly. Thorne took the question seriously. In 1988, he and colleagues published work demonstrating that traversable wormholes could exist theoretically under certain conditions. A traversable wormhole means a stable passage through which matter could move safely from one location to another. But stability required something familiar: exotic matter again. Without negative energy density supporting the throat, gravity would force the tunnel shut instantly. The same obstacle haunting warp drives reappeared here through a different geometric form. General relativity permitted the structure mathematically, yet ordinary matter could not hold it open. Still, wormholes differ fundamentally from warp bubbles operationally. A wormhole connects fixed points in spacetime. You do not steer continuously during transit. You enter one mouth and emerge elsewhere through another already existing endpoint. In practical terms, that implies infrastructure requirements at both locations in advance. You must know where the exit is and somehow establish it. But the story became stranger in 2013 when physicists Juan Maldacena and Leonard Susskind proposed a conjecture now known as ER equals EPR. The initials combine Einstein-Rosen bridges with Einstein-Podolsky-Rosen quantum entanglement pairs. The proposal was radical. They suggested quantum entanglement and wormholes may represent two descriptions of the same underlying phenomenon: entangled particles, pairs linked through correlated quantum states, regardless of separation distance, might actually remain connected geometrically through microscopic wormholes invisible at observable scales. Entanglement could literally be geometry. This idea remains speculative, but it occupies serious theoretical territory at the intersection of quantum information theory and quantum gravity research. Physicists continue exploring whether spacetime itself emerges from patterns of entanglement woven through deeper quantum structures. If ER equals EPR proves fundamentally correct, then the quantum vacuum changes character dramatically. Empty space already seethes with virtual particles, constantly becoming entangled and disappearing again. Beneath apparent emptiness, reality may contain an enormous foam of microscopic wormholes flickering continuously at Planck scales. The question then shifts subtly, not whether wormholes exist, but whether any intelligence could ever enlarge one enough to cross. Eventually, every serious conversation about warp drives arrives at the same boundary: not an energy limit, not an engineering obstacle, a deeper absence. We still do not possess a complete theory of gravity at quantum scales. General relativity describes the large structure of reality extraordinarily well. It predicts black holes, gravitational lensing, time dilation, and the expansion of the universe with astonishing precision. On cosmic scales, Einstein's equations remain among the most successful scientific ideas ever created. But the theory breaks down eventually. At distances approaching the Planck scale, roughly 10 raised to the negative 35th meters, quantum effects become impossible to ignore. Spacetime itself may fluctuate violently there, losing the smooth geometric behavior general relativity assumes. Quantum mechanics governs that microscopic world instead. Quantum theory describes particles, fields, probability amplitudes, and atomic interactions with unmatched accuracy. Every modern electronic device, laser, and semiconductor relies on equations derived from quantum mechanics functioning correctly. Yet quantum theory has its own weakness. Gravity barely fits inside it. When gravitational fields become extremely intense, such as near black hole singularities or during the first moments after the Big Bang, quantum mechanics and general relativity stop cooperating mathematically. The equations become incompatible. Both theories work astonishingly well separately, but together they fracture. One of them is incomplete, possibly both. This unresolved conflict matters directly for warp drive physics because exotic matter, vacuum fluctuations, and spacetime geometry all occupy the boundary region where gravity and quantum behavior intersect simultaneously. Several candidate frameworks attempt to bridge the divide. String theory remains the most widely known. It proposes that fundamental particles are not point-like objects, but tiny vibrating, one-dimensional strings whose oscillation patterns generate different particle properties. The mathematics naturally incorporates gravity, but only if additional spatial dimensions exist beyond the familiar three, usually 10 or 11 total dimensions. Most remain hidden from direct observation. Another major approach is loop quantum gravity. Instead of adding extra dimensions, it treats spacetime itself as quantized, composed of discrete, microscopic units woven into network like structures at the Planck scale. Space may not be continuous fundamentally at all. It may come in indivisible chunks. If either framework proves correct, our understanding of exotic matter could change dramatically. Negative energy density may turn out easier to generate under certain quantum gravitational conditions, or completely forbidden beyond tiny fluctuations. The answer depends on the true microscopic architecture of spacetime itself. And right now, we do not know that architecture. This uncertainty cuts both directions equally. Quantum gravity might ultimately eliminate warp drives entirely by revealing hidden consistency conditions, preventing stable spacetime distortions. The loophole may close once deeper physics becomes visible. But the opposite possibility also exists. Entire categories of matter, vacuum behavior, or geometric manipulation inaccessible to classical physics may emerge naturally from a successful quantum gravity theory. We cannot predict which outcome awaits. That is the strange position modern physics occupies tonight. Humanity is discussing how to engineer spacetime while lacking a complete understanding of what spacetime fundamentally is. We know how it bends macroscopically. We know how quantum fields behave microscopically. But the bridge between those descriptions remains unfinished, which means warp drive research exists balanced between ignorance and discovery, resting on a frontier where the next major breakthrough in physics could either extinguish the idea permanently or transform it completely overnight. A microscopic warp bubble, if it ever appeared inside a laboratory, would not look dramatic. No visible distortion would ripple through the air. No glowing field would surround the apparatus. The effect would be smaller than anything human senses could perceive directly. So the question becomes methodological. How do you detect geometry itself changing? Modern physics already possesses one answer: interferometry, a measurement technique based on splitting light into separate paths and comparing how the returning waves interfere with one another. If spacetime stretches or compresses even slightly along one path, the recombined light pattern shifts. Tiny changes become measurable. This principle reached extraordinary precision through LIGO, the Laser Interferometer Gravitational Wave Observatory. In 2015, LIGO detected gravitational waves generated by two black holes colliding roughly 1.3 billion light years away. The distortion reaching Earth was almost unimaginably small. LIGO measured space-time fluctuations less than 1,000th the diameter of a proton across laser paths 4 kilometers long. The achievement transformed gravitational waves from theoretical prediction into directly observed reality, and it changed the psychology surrounding space-time measurement permanently. Before LIGO, many distortions predicted by general relativity remained effectively invisible experimentally. Afterward, humanity possessed instruments sensitive enough to detect geometry itself flexing across cosmic distances. That mattered deeply for warp research. Harold White's Eagleworks experiments attempted a miniature version of this strategy. Instead of waiting for colliding black holes, the laboratory tried generating hypothetical local distortions using charged electromagnetic systems arranged around ring-shaped capacitors. Then they searched for altered light paths. The difficulty was brutal. At laboratory energy scales, any hypothetical warp-related effect would be extraordinarily weak, buried beneath countless environmental disturbances. Thermal expansion changes material dimensions constantly. Passing vehicles create seismic vibrations, electrical systems fluctuate microscopically, even footsteps influence precision measurements. Signal and noise begin resembling one another. Separating them becomes the experiment itself. Future detection systems may improve those conditions dramatically. One important step already exists in development: the Laser Interferometer Space Antenna, usually called LISA, scheduled for launch during the 2030s. LISA will place multiple spacecraft millions of kilometers apart in solar orbit, creating a space-based interferometer far larger than anything possible on Earth. And quieter. Earth's seismic background disappears in deep space. No tectonic movement, traffic vibrations, atmospheric turbulence, or local thermal disturbances interfere with measurements there. LISA is primarily designed to detect lower frequency gravitational waves from enormous cosmic events inaccessible to LIGO. But the instrument's sensitivity may extend beyond its original mission. Some physicists speculate that future interferometers derived from LISA technology could search for microscopic, exotic space-time geometries or vacuum fluctuations associated with advanced propulsion research. Nothing confirmed exists yet, but the measurement capability itself continues advancing rapidly. That broader trend matters more than any single experiment. Alcubierre published his paper in 1994, 18 years before humanity detected its first gravitational wave. During that short interval, our ability to measure space-time distortions improved by orders of magnitude previously unimaginable. Each increase in precision changes which questions become experimentally accessible, and physics often advances when instruments finally become sensitive enough to notice what theory predicted long before technology could observe it. Imagine, for a moment, that the physics problem is solved. Exotic matter exists in usable quantities. Stable warp geometries become possible. The equations hold. The laboratory evidence survives scrutiny. A different set of problems appears immediately afterward. Engineering begins. A practical warp system would likely center around a ring or toroidal structure surrounding the spacecraft, something resembling a massive circular framework wrapped around the hull. Inside that structure, field emitters would generate and shape the space-time distortion defining the warp bubble itself. The geometry would require extraordinary precision. Tiny asymmetries in the field distribution could destabilize the bubble or alter its trajectory unpredictably. Unlike ordinary propulsion systems, the engine would not push against surrounding matter. It would manipulate space-time curvature directly around the vessel. The power demands remain staggering. No existing energy technology approaches the scales discussed in serious warp literature. Chemical rockets become irrelevant instantly. Even nuclear fusion may prove insufficient. One candidate often discussed is matter-antimatter annihilation because it converts mass into energy with nearly perfect efficiency according to Einstein's equation relating energy and mass. The numbers become difficult to grasp. 1 kilogram of antimatter annihilating with 1 kilogram of ordinary matter releases approximately 1.8 multiplied by 10 raised to the 17th joules of energy, comparable to roughly 43 megatons of explosive yield. But antimatter introduces its own nightmare. Humanity currently produces antimatter atom by atom inside particle accelerators at enormous expense. Estimates place production costs near $62.5 trillion per gram under current technology. Containing antimatter safely also requires elaborate electromagnetic traps because contact with normal matter causes immediate annihilation. And propulsion is only the beginning. Navigation becomes profoundly dangerous at effective, faster than light speeds. Because the crew cannot communicate with the leading edge of the warp bubble during transit, destination coordinates must be calculated beforehand with extraordinary accuracy. Errors compound catastrophically. A tiny navigational mistake across interstellar distances could redirect arrival points by astronomical margins. Worse still, the bubble cannot easily detect hazards ahead because information from the forward region cannot outrun the bubble itself locally. Interstellar space is not perfectly empty. Gas atoms, dust grains, and microscopic particles drift between stars constantly. A warp bubble moving through contracting spacetime may accumulate these particles along its forward boundary. Several theoretical studies suggest that upon deceleration, the trapped material could release enormous bursts of high-energy radiation, potentially gamma rays. In 2012, physicists at the University of Sydney calculated that a warp vessel arriving from even 10 light-years away might discharge radiation intense enough to sterilize the destination region if uncontrolled. A functioning warp drive could also become an accidental weapon. Another issue appears inside the bubble itself. Heat. Ordinary spacecraft radiate excess thermal energy into surrounding space continuously, but a warp bubble partially isolates its interior from normal spacetime geometry. Heat generated by computers, life support systems, reactors, and human bodies may become difficult to remove efficiently. The ship risks cooking internally. None of these problems prove warp travel impossible, but they reveal something important. Once the exotic matter question moves aside, the remaining obstacles resemble engineering crises rather than violations of physical law. And engineering problems, historically, are the kinds humanity eventually learns how to solve. In 1895, Lord Kelvin stood among the most respected physicists on Earth. He helped formulate the laws of thermodynamics, calculated the age of the planet, and shaped modern physics profoundly. When Kelvin spoke publicly about science, people listened carefully, and Kelvin believed heavier than air-flying machines were impossible. 8 years later, two bicycle mechanics lifted a fragile wooden aircraft into the air at Kitty Hawk for 12 seconds. The age of aviation began almost immediately afterward, not because physics changed suddenly, but because engineering finally crossed a threshold where theory and machinery aligned. History contains several moments like this. In 1933, physicist Ernest Rutherford dismissed the idea of extracting useful energy from atoms as moonshine. Rutherford had discovered the atomic nucleus itself. If anyone understood atomic structure deeply, it was him. But 12 years later, on July 16th, 1945, the Trinity test detonated in the New Mexico desert. Human civilization entered the nuclear age through engineering advances layered upon already existing physical principles. Then the pattern repeated again. In 1945, Vannevar Bush, who directed American wartime scientific research during the Second World War, testified before the United States Senate that intercontinental ballistic missiles were effectively impractical. The engineering barriers appeared overwhelming. 12 years later, Sputnik orbited Earth. The point is not that scientists are foolish. Quite the opposite. When physicists describe something as impossible, they usually mean impossible according to current understanding, available materials, known energy scales, or achievable engineering precision. Science progresses by tightening those constraints carefully, not by ignoring them recklessly. And many impossible ideas remain impossible permanently. Perpetual motion machines violate thermodynamics directly. Faster than light particles, moving locally through space, violate special relativity explicitly. Those concepts collide headfirst with foundational physical laws tested repeatedly through experiment. Warp drives occupy a different category. The Alcubierre metric does not require objects to outrun light locally through surrounding spacetime. It operates within Einstein's gravitational framework rather than against it. The equations remain mathematically consistent under general relativity itself. The obstacle lies elsewhere. Exotic matter, negative energy density, spacetime engineering at scales far beyond present technology. That distinction matters because the historical transitions from impossibility to achievement often involved engineering accumulation rather than revolutions in fundamental physics. Airplanes did not require new physical laws beyond fluid dynamics and combustion. Nuclear weapons did not overturn atomic theory. Rockets did not rewrite gravity. Humanity simply reached sufficient precision, energy control, material science, and manufacturing capability gradually over time. Thresholds shifted. Warp research may ultimately fail because exotic matter proves fundamentally inaccessible outside microscopic quantum effects. The universe may contain hard barriers beyond which no engineering effort can pass. That possibility remains entirely real. But history also warns against assuming current technological limitations define permanent cosmic boundaries automatically, especially in physics. A civilization powered by 19th century machinery could not meaningfully evaluate nuclear engineering. Likewise, a civilization still struggling to sustain fusion reactions may not yet possess the conceptual or technological tools needed to manipulate spacetime deliberately. So, the central question remains unresolved tonight. Is exotic matter a true physical wall built into reality itself, or merely another threshold waiting for a future technology sophisticated enough to cross it? For most of human history, power belonged to whoever moved fastest across distance. Empires expanded along coastlines first, then along railways, then through skies and communication networks. Every transportation revolution reorganized civilization afterward, sometimes gradually, sometimes violently. Geography changed, economies shifted, entire political systems lost relevance almost overnight. Interstellar capability would magnify that pattern beyond anything in recorded history. The first civilization, nation, alliance, or corporation to develop even limited warp technology would gain access to resources so vast they barely fit within ordinary economic language. Wealth on Earth has always depended partly on scarcity, but space changes the arithmetic completely. The asteroid belt alone contains extraordinary reserves of nickel, platinum, cobalt, iron, and rare metals. Some economic estimates place its theoretical mineral value near $700 quintillion, enough to represent roughly $93 billion for every person alive today. And the asteroid belt is nearby. Far beyond Neptune drifts the Oort cloud, a diffuse shell of icy bodies surrounding the solar system at distances reaching approximately 3.2 light years. Astronomers estimate it may contain nearly 2 trillion objects, preserved remnants from the solar system's formation over 4.5 billion years ago. Each one contains material, fuel, water, carbon compounds, future infrastructure. But resources alone are not the deepest implication. Proxima Centauri b orbits within the habitable zone of the nearest star to our own. If conditions there support biology, even microbial biology, humanity would encounter a completely separate evolutionary experiment. A second origin of life would transform medicine, genetics, evolutionary theory, and perhaps our understanding of consciousness itself. Nothing in human history compares cleanly to that moment, and none of our current political systems are designed for it. The geopolitical structure of Earth has always been shaped by transportation technology. Sailing ships created colonial empires. Railroads unified continents economically. Aircraft compressed warfare into hours instead of months. Digital networks erased communication delay almost entirely. Warp capability would continue the same pattern, only now across stars. But there is no functioning interstellar governance model waiting quietly in reserve. No legal framework exists for ownership, migration, extraction rights, biological contamination, or territorial disputes between star systems. Humanity has not resolved these questions even on Earth itself. The Outer Space Treaty of 1967 attempted to prevent national appropriation of celestial bodies, including the moon and planets. It was visionary for its time. But it emerged during the Cold War, when reaching another star remained effectively impossible even theoretically. Its language belongs to an earlier technological era, and treaties only function while participants agree to obey them. A civilization possessing warp capability before everyone else may gain decades, centuries, or longer of uncontested expansion. That imbalance would exceed any historical naval advantage or nuclear monopoly. Distance itself would stop protecting weaker societies entirely. So, beneath the physics sits another question quietly waiting. When humanity finally reaches outward seriously, will we travel as a coordinated species sharing a common future? Or will we arrive among the stars carrying the same rivalries that shaped every frontier before them? The night sky once looked empty because we lacked the instruments to see properly. Now the darkness is crowded. As of 2024, astronomers have confirmed more than 5,500 exoplanets beyond our solar system. Most were discovered through the Kepler and TESS space telescopes, which watched distant stars for tiny rhythmic dimmings caused by planets crossing in front of them. The important realization arrived quietly. Planets are not unusual accidents. They appear to form almost everywhere stars do. Kepler data suggests the Milky Way alone may contain roughly 40 billion Earth-sized planets orbiting within habitable zones around stable stars. A habitable zone simply means temperatures may allow liquid water on a planetary surface. But habitability and familiarity are not the same thing. Some worlds may have oceans beneath ice instead of beneath clouds. Others may never see sunlight at all. Europa, one of Jupiter's largest moons, sits nearly 390 million miles from Earth. Beneath its frozen crust lies a global ocean kept liquid through tidal heating, the gravitational squeezing produced by Jupiter's immense pull. Scientists estimate Europa's hidden ocean may contain more than twice the volume of all Earth's oceans combined. And Europa is only one moon. Enceladus, orbiting Saturn, vents water vapor and organic molecules directly into space through fractures near its south pole. The Cassini spacecraft flew through these plumes repeatedly between 2005 and 2017, detecting salts, hydrocarbons, and evidence of hydrothermal activity beneath the ice. Warm water, chemistry, energy, the ingredients matter, because life on Earth has proven disturbingly adaptable. Microorganisms survive around hydrothermal vents deep beneath the ocean floor where sunlight never reaches. Others persist inside Antarctic ice, within highly acidic springs, and high in the upper atmosphere where radiation levels become lethal to most complex organisms. Every decade expands the definition of where biology can exist. But once that boundary widens enough, the galaxy begins changing shape in our imagination. Empty space starts feeling less empty. Silence becomes uncertainty rather than absence. If even microbial life exists independently on Europa or Enceladus, then biology may emerge wherever conditions permit it. That would imply the Milky Way is not mostly sterile, but chemically alive in ways we have barely started recognizing. A functioning warp capability would eventually test that possibility directly, and the first confirmed discovery of extraterrestrial life, even microscopic life, would alter human thought more profoundly than any political revolution or technological invention in recorded history. Religion, philosophy, medicine, biology, and law would all shift simultaneously, because another living system is not just another object, it possesses interests, its own evolutionary history, its own continuity. So the moment of arrival at another inhabited world would not only be scientific, it would also become ethical immediately. We would face questions no civilization has ever answered before in practice. Do untouched ecosystems possess rights? Can contamination ever be justified? If intelligent life exists, who speaks first? And what if their understanding of morality evolved along completely different biological lines from ours? Imagine crossing interstellar distance at last, entering another planetary system after months inside engineered spacetime, only to find silence again. No signals, no biology, no ruins beneath alien skies, just rock, ice, atmosphere, and chemistry repeating endlessly across light years. That possibility carries its own weight. We often imagine discovery as confirmation that life fills the cosmos abundantly, but there is another outcome waiting quietly beside it. A future where system after system appears promising from afar, then resolves into sterility once examined closely. Proxima Centauri b could be barren. The planets of TRAPPIST, one could hold oceans without organisms. Even worlds rich in carbon compounds and liquid water may never cross the threshold into biology at all. And if that pattern continues repeatedly, the implications begin changing shape. In 2000, paleontologist Peter Ward and astronomer Donald Brownlee popularized the rare Earth hypothesis, arguing that complex life may require an extraordinarily narrow chain of conditions occurring simultaneously over immense spans of time. Not just liquid water, but stable plate tectonics recycling nutrients through the crust. a large moon stabilizing axial tilt over geological ages, magnetic shielding against stellar radiation, a Jupiter-class outer planet diverting catastrophic comet impacts. Even location inside the galaxy matters. Too close to the crowded galactic center and radiation intensifies. Too far outward and heavy elements become scarce. Earth may occupy an unusually narrow corridor where complexity could survive long enough to evolve intelligence. If that hypothesis is even partly correct, then the silence surrounding us stops looking mysterious. It becomes expected. The Milky Way contains hundreds of billions of stars, yet intelligence may still emerge only once, or almost once, across its entire history. Consciousness capable of mathematics, language, memory, art, and existential reflection may not be evolution's normal outcome. It may be a statistical anomaly, but if humanity eventually develops warp capability and explores the galaxy directly, we would no longer speculate from telescopes alone. We would test the silence physically, world by world, ocean by ocean, atmosphere by atmosphere, and imagine what that realization would feel like after decades of searching. Not that life is rare, that we may be alone entirely. Not temporarily alone, absolutely alone. Carl Sagan once described Earth as a lonely speck in the great enveloping cosmic dark. At the time, humanity had not even reached another planet with human beings, much less another star. The statement carried uncertainty inside it. Hope still occupied the silence. But a warp-capable civilization could eventually answer the question directly. And either answer changes us permanently. Finding life would mean consciousness blooms naturally throughout the cosmos, but finding nothing would place extraordinary responsibility onto our species. Every poem, every memory, every act of kindness or cruelty, every scientific insight, every piece of music ever composed would belong to the only known arrangement of matter in the universe that became aware of itself. The galaxy would stop feeling crowded with possibilities and start feeling unbearably dependent on whether humanity survives long enough to carry awareness farther into the dark. A physicist standing in the year 1800 would have believed the universe was nearly understood. Gravity was known, motion was known, the planets followed predictable paths across the sky, light existed, electricity existed, magnetism existed, nature appeared orderly and increasingly complete. But James Clerk Maxwell had not yet unified electricity and magnetism into a single framework. Electromagnetism, one of the fundamental forces shaping modern civilization, still existed as disconnected observations waiting for someone to recognize the pattern. That recognition arrived 65 years later, and the shocks continued. A scientist, standing in 1900, still knew nothing about quantum mechanics, nuclear decay, black holes, or space-time curvature. Radioactivity had barely entered scientific awareness. Einstein had not yet rewritten gravity. Quantum uncertainty, the idea that particles possess probabilities rather than fixed positions, would have sounded absurd. The entire 20th century physics revolution remained invisible from the threshold of the century itself. That history matters, because it reminds us that scientific confidence often expands directly beside scientific blindness. Every generation believes the remaining mysteries are small. Then, reality opens again. The honest position is uncomfortable. We do not know what we do not know. Even now, modern cosmology admits that most of the universe remains unexplained. Observations of galactic rotation curves during the 1930s revealed something strange. Galaxies rotate too quickly to remain gravitationally stable based only on visible matter. Something unseen contributes additional mass. That unknown component became known as dark matter. Today, measurements from the Planck satellite suggest dark matter accounts for approximately 27% of the universe's total mass energy content. Yet, after nearly 90 years of study, its fundamental nature remains unknown. We infer its existence through gravity alone. Then there is dark energy. In 1998, astronomers studying distant supernovae discovered that cosmic expansion is accelerating rather than slowing down. Something appears to be pushing spacetime outward on the largest scales. That phenomenon now accounts for roughly 68% of the universe. Combined, dark matter and dark energy constitute approximately 95% of reality, and we cannot explain either one fully. We cannot isolate them directly. We cannot engineer them, but they dominate the cosmos anyway. So claims that space-time engineering must be impossible begin sounding less definitive against that background. It may simply be too early in the history of physics to know where the actual boundaries lie. The exotic matter problem could remain permanently insurmountable. Negative energy density may prove impossible to stabilize macroscopically. Quantum gravity might ultimately forbid warp geometries entirely. But future frameworks may reveal something else instead. Dark energy itself may eventually connect to vacuum structure in ways we do not yet understand. Quantum gravity could uncover mechanisms hidden completely outside current mathematics. Entire categories of physical behavior may still wait undiscovered beneath scales we cannot probe yet. We are attempting to understand space-time while missing most of the universe's inventory, and that realization changes the emotional shape of the question, not because it guarantees warp travel, but because it reminds us that the frontier separating impossible from undiscovered has moved many times before, often without warning, and usually long before anyone recognized it was about to move again. A warp drive changes the scale of distance. It does not erase distance entirely. Even traveling at 10 times light speed, the crossing to Proxima Centauri would still require roughly 5 months. The stars remain far apart. Space remains enormous. Human beings would still spend long stretches suspended between origins and destinations, moving through regions where almost nothing exists. Interstellar space is difficult to picture accurately from Earth. There would be no nearby planet brightening the darkness, no moon, no atmosphere scattering light across a horizon. The sun itself would shrink into another star among thousands, brilliant but emotionally detached from the role it played throughout human evolution. And communication would slow immediately. A message sent from Proxima Centauri back to Earth would still travel no faster than light once it left the warp field. The transmission delay alone would exceed 4 years each way. A simple question asked from the ship could require more than 8 years before an answer returned. Conversations would stop behaving like conversations. The crew would become informationally isolated from humanity in a way no explorers ever were before. Antarctic researchers still speak with home daily. Submarine crews eventually surface. Even astronauts aboard the International Space Station remain only milliseconds away from Earth conversationally. But interstellar travelers would drift beyond real-time human contact entirely. We already understand part of what prolonged isolation does psychologically. Antarctic winter overstudies, long submarine deployments, and the Mars 500 simulation in Moscow all revealed similar patterns. Confinement alters emotional regulation. Sensory monotony changes sleep cycles and attention. Small social tensions intensify under repetition and delay. Time begins feeling strangely elastic. The first interstellar crews would carry those pressures farther than any humans before them. They would exist beyond rescue capability, beyond immediate instruction, beyond the possibility of external intervention if systems failed or conflict emerged. Every decision would belong only to them, and the visual experience outside the ship would become increasingly unfamiliar with distance. Constellations depend entirely on perspective. Move far enough away, and the sky rearranges itself. Orion dissolves. The Southern Cross distorts. Ancient navigation patterns, built across thousands of years, disappear gradually into new geometries. From interstellar space, the Milky Way itself would begin changing appearance. Instead of seeing the galaxy from deep inside one spiral arm, travelers would slowly perceive its larger structure, a luminous band stretching across darkness with a shape no human nervous system evolved to witness directly. That transformation matters because human consciousness formed under very specific environmental assumptions: a nearby sun, a stable horizon, immediate communication with one another, familiar skies repeating season after season across generations. Interstellar travel removes all of those anchors simultaneously. But something continues traveling with the crew regardless. Language remains. Memory remains. So do affection, grief, curiosity, fear, and the strange human habit of telling stories while crossing darkness. The first people between stars would carry no permanent physical connection to Earth around them anymore. Only the internal one, and for months at a time, that invisible continuity may become the only surviving bridge between humanity's past and whatever waits ahead in the blackness beyond the Sunday. Long before physics described spacetime mathematically, human beings were already trying to cross it in stories. Ancient cultures filled the night sky with hunters, rivers, animals, ancestors, and gods. The stars were never treated as decoration alone. People projected meaning onto them instinctively, even when the distances involved remained unimaginable. Across continents separated by oceans and centuries, civilizations still looked upward and asked similar questions. What is out there? And why are we here beneath it? That impulse survived every technological era afterward. Navigation by stars carried ships across unknown oceans. Early telescopes transformed wandering points of light into worlds. Fiction imagined journeys long before engineering could approach them. The desire arrived first, the mathematics followed later. Even the 20th century space programs reflected something deeper than practical economics. The Apollo program cost roughly $280 billion in modern terms. No direct financial return justified it. The moon contained no urgent military target by the mission's end, no recoverable resource large enough to balance the expense. Yet millions of people watched anyway because the achievement satisfied something difficult to quantify. A species that evolved on one world briefly stepped onto another. That mattered emotionally. The Voyager probes carried the same instinct outward more quietly. Launched in 1977, Voyager 1 and Voyager 2 now move through interstellar space, carrying golden phonograph records filled with sounds and images from Earth. Greetings in dozens of languages, music, human laughter, wind, rain, heartbeats. The records were designed partly by Carl Sagan and his team as messages for whoever might someday encounter them. The probability of discovery remains extraordinarily small. The nearest stars are unimaginably distant, and the probes travel without any realistic expectation of interception. But we sent them anyway, not because success was likely, because reaching outward felt necessary. New Horizons continued that pattern decades later. After flying past Pluto in 2015, the spacecraft continued toward the outer solar system, carrying a small capsule containing the ashes of Clyde Tombaugh, the astronomer who discovered Pluto in 1930. Even our dead continue traveling outward now. We send pieces of ourselves into darkness before we can physically follow. Machines first, names first, voices first, symbols first. The warp drive, if realized someday, would not create this impulse. It would merely fulfill a trajectory already visible across human history. Every generation inherits the same horizon and then pushes slightly farther beyond it. But there is another layer beneath the engineering problem. Civilizations are not guaranteed permanence. Climate instability, nuclear conflict, ecological collapse, pandemics, artificial intelligence, and resource exhaustion all exist within the same century that contemplates interstellar travel. The question is not only whether warp physics can eventually function, it is whether humanity remains coherent long enough to solve problems requiring patience measured across generations. That answer does not emerge from equations. Physics can describe energy, geometry, and spacetime curvature. It cannot determine whether societies choose long-term thinking over immediate conflict. It cannot force cooperation, curiosity, or restraint. Those decisions belong elsewhere, and perhaps that is the deeper meaning hidden beneath all this machinery. The stars are not simply testing our intelligence. They are testing whether intelligence alone is enough to carry a civilization safely beyond the world that created it. By early 1990, Voyager 1 had already crossed beyond the orbit of Neptune. The spacecraft was moving outward at more than 38,000 miles per hour, carrying instruments built by a civilization still divided by borders, languages, and ideologies. Behind it stretched the entire planetary system that created it. Ahead, almost nothing. At Carl Sagan's request, NASA commanded Voyager 1 to turn its camera backward one final time before its imaging systems were shut down permanently to conserve power. From roughly 3.7 billion miles away, the spacecraft captured a frame that would become one of the most unsettling photographs in human history. Earth appeared as less than a single pixel, a tiny speck suspended inside a shaft of scattered sunlight crossing the camera lens. Not blue in any recognizable sense, not detailed, barely visible at all. Yet everything familiar existed there. Every empire, every language, every religion, every scientific breakthrough and private heartbreak, every war fought across deserts, forests, islands, and oceans, every parent holding a child, every species humanity has ever loved or erased, all contained within something smaller than dust inside the image. Sagan later wrote that the photograph underscored the folly of human conceits. Distance had stripped Earth of psychological scale. Seen from far enough away, the arguments that consume civilizations become visually indistinguishable from silence. But interstellar travel changes the meaning of that image again. A civilization capable of crossing the gulf between stars would eventually produce another photograph like it, this time from the vicinity of another sun. From Proxima Centauri b, Earth would vanish entirely to unaided vision. Our planet would disappear into the glare surrounding a modest yellow star among countless others. The sun itself would appear with an apparent magnitude near zero point 0.4, bright enough to notice, ordinary enough to ignore. Nothing about it would announce that intelligent life orbited there. If observers stood on a distant world tonight and looked toward our region of the galaxy, they would see no evidence of humanity at all. Our radio signals have only traveled a little more than 100 light years outward since the early 20th century. Beyond that sphere, Earth remains historically silent. Invisible civilizations do not feel invisible from the inside. That may be one of the strangest realizations hidden within astronomy. entire histories can unfold without leaving detectable traces across interstellar distances. For thousands of years, every triumph and catastrophe in human civilization occurred beneath a sky completely indifferent to whether we existed. But a functioning warp drive would alter that relationship permanently. Not because it would make humanity important cosmically. The universe is too large for that. But it would allow human activity to propagate outward faster than passive light and radio leakage alone. Physical presence would begin replacing observation. The first interstellar mission would therefore represent more than transportation technology. It would mark the moment human existence ceased being confined to one isolated atmosphere around one ordinary star. For the first time since life emerged on Earth, awareness itself would begin moving deliberately between suns. For more than 30 years, physicists have searched for the hidden error inside the Alcubierre metric. They have tested the assumptions, challenged the geometry, questioned the energy conditions, and traced the implications through causality, quantum theory, and cosmology. The loophole survived, not proven practical, not proven buildable, but still present. Inside Einstein's equations sits a solution that appears to permit effective, faster than light travel without locally violating special relativity. The mathematics remains internally consistent. Peer-reviewed papers continue refining it. Entire branches of theoretical work now exist because one physicist decided in 1994 to stop treating warp drive as fiction and ask whether the equations themselves objected. They did not, but the equations asked for something else instead. Energy scales beyond anything civilization currently controls. Forms of matter never produced macroscopically. Precision engineering measured against the structure of spacetime itself. Patience extending across generations of researchers who may never see the final result of their work. Real thresholds usually look like this at first. The first electrical experiments in the 18th century did not resemble a planetary communication network. Early steam engines barely functioned before reshaping industrial civilization. The Wright brothers remained in the air for only 12 seconds at Kitty Hawk in 1903. 66 years later, human beings walked on the moon. Progress rarely arrives fully formed. It accumulates quietly through tools and discoveries that initially appear disconnected from the destination they eventually create. Some future physicist may discover that exotic matter cannot exist in stable quantities. The door could close completely. Quantum gravity may reveal a hidden contradiction inside every warp metric. Nature is under no obligation to make interstellar travel achievable. But the opposite remains possible too. The exotic matter problem may dissolve inside a deeper framework of physics not yet understood. Negative energy densities may become engineerable through mechanisms still invisible to present theory. A civilization centuries from now may look back at our understanding of spacetime the way modern chemistry looks back at medieval alchemy, recognizing fragments of truth surrounded by vast missing structures. We do not know. That uncertainty is the entire point. The universe did not hand humanity a map to the stars. It handed us equations that leave the question open. A narrow mathematical opening exists between impossible and permitted, small, difficult, fragile, but real, and that changes something profound. Because once a door exists in principle, history suggests human beings eventually try to cross it. Not always wisely, not always successfully, but persistently. Tonight, somewhere above you, light from distant stars is crossing the dark exactly as it has for billions of years. Most of those worlds will never know we existed. Some may already hold ruins older than Earth itself. Others may still be waiting for oceans to cool. And here you are, alive during the brief moment when a species confined to one planet first realized the laws of physics may not entirely forbid the journey between them.